Hi everyone, welcome to the presentation of our paper, Analogy Forming Transformers for Few-Shot 3D Parsing. Given a 3D object, predicting its decomposition into parts has been traditionally addressed by training a neural network that maps the input to segments. Given enough labeled examples, a neural network can parse diverse object structures and categories by storing in its weights a direct mapping from the input to part segments. But what if after training we encounter an instance of a new object category we have not seen before? We need to collect a relatively large set of annotated examples and retrain our network via slow gradient descent weight updates. Humans can quickly adapt to novel categories even from a single example. Can we push the limits of today's neural networks to the incredible human adaptation ability? We propose analogical networks, which are parametric neural networks augmented with associative memories. Specifically, a labeled experience, which we call memory, primes an analogy-driven prediction. Our model, instead of mapping the input to part segments directly, maps it to modifications and compositions of retrieved relevant labeled past experiences. Different memories prime different part predictions, here of coarser or finer segmentations of the input shared. In this way, multiple outputs can be predicted by changing the conditioning memories. Our model is comprised of a retriever and a modulator. Given a 3D input scene, the retriever finds the relevant memories and the modulator predicts the analogous part structure. In more detail, the retriever has access to a large bank of annotated previous examples. We encode each memory in the input scene with the same encoder and use K and N to find relevant memories. The modulator jointly encodes the input scene and the retrieved labeled memories. Each part segment in our retrieved memory is encoded into a query vector that is used as a slot to decode analogous parts in the input point cloud. We also use a set of scene-agnostic query vectors to segment things that are not present in the retrieved memory set. When a memory part query is used to decode an input part, we say that the two parts are put into correspondence. Intuitively, we expect that memory part queries will decode analogous parts. For example, a chair seat in the memory will decode the chair seat in the input scene. Can this part correspondence emerge without semantic supervision? We devised a novel within-scene pre-training scheme to promote correspondence between the input and the memory parts. Given a training scene, we create two augmented views, one of them acting as the input and the other as the memory. Here, we have ground truth information of which memory query corresponds to each input segment, and we supervise the assignment. We show that this suffices to establish cross-scene correspondence as well. After within-scene pre-training, we train cross-scene, where the memory and input are different examples. We use the weights of the within-scene pre-trained modulator encoder to initialize the retriever encoder and keep it frozen during training. The modulator weights are initialized from the within-scene pre-trained weights and are further optimized cross-scene. The model is trained for part segmentation by assigning the decoded part segments to ground truth part segments via Hungarian matching, much like a standard segmentation transformer. We evaluate our approach on PartNet, a dataset with object part annotations of different levels of granularity. We train on a set of 12 classes and keep a set of 4 classes that are unseen during training. We evaluate our performance on 3 setups: a standard many-shot on the test set of the training classes, few-shot on the test set of the novel classes, assuming that few samples are given for them, few-shot with fine-tuning on the test set of the novel classes after fine-tuning of the few given examples. We compare analogical networks to the following baselines. First, we compare with a model that attends to memory but does not use it as queries to decode parts. We call this model Redeter3D, a retrieval augmented detection transformer. Next, we remove the memory and replace it with a learnable embedding used to communicate to the model the task, for example, the segmentation level. This baseline is called Deter3D. We first evaluate the ability of our approach to segment objects into parts without using or predicting semantic labels. The metric is ARI, a clustering metric, the higher the better. We observe that the many-shot performance is comparable for all variants of our model, largely outperforming PartNet, a state-of-the-art segmentation network. In few-shot, analogical networks largely outperform all competitors. Specifically, even without fine-tuning, analogical networks outperform DETR3D, even when this is fine-tuned on the novel classes. Additionally, they outperform DETR3D on all setups, showing that explicitly decoding correspondences is useful. Lastly, DETR3D outperforms DETR3D, showing the importance of memory for few-shot parsing. We then measured the ability of our model to propagate labels at test time through corresponding parts, despite never seeing labels at training time. More specifically, memory parts that are put into correspondence with an input part transfer their label directly to the input part. For reference, we compare to DETR3D fully supervised for label prediction. Analogical networks achieve reasonable performance on all tested setups. We additionally compared against our model without within-scene pre-training, which performs very poorly, indicating the importance of within-scene pre-training for cross-scene correspondence. Lastly, the multi-memory model outperforms the single-memory version, as it has access to a more diverse set of memory queries and thus uses them more often. Qualitatively, we observe that analogical networks learn fine-grained correspondences between parts of the input and the memory, which are visualized here with the same color. When there is no corresponding memory part to explain an input part, as with regions with black color in the third column, scene-agnostic queries decoded, as seen in the fourth column. Analogical networks generalize cross-scene correspondences to objects of novel classes as well. Here, we visualize results without fine-tuning on novel classes. Additionally, analogical networks can find geometric correspondences between objects of different categories. Next, we qualitatively examine the behavior of the retriever. We can see that it does not focus on the class only, but rather mostly on the geometry. To summarize, analogy-driven prediction asks what an object is like as opposed to what it is. We find that analogically inferring the label space leads to faster few-shot adaptation. It also unifies many-shot and few-shot inference by retrieving memories from the appropriate set. Lastly, the task information is communicated via the memory labels, essentially supporting dynamic multitasking. Thank you for your attention. Our code is publicly available on our website.